Welcome to this video on blockchain. In this video, we're going to be going over some of the basics and some important topics that you might need to know. So, what is a blockchain? According to Ethereum.org, a blockchain is a database of transactions that is updated and shared across many computers in a network. Every time a new set of transactions is added, it's called a block, hence the name blockchain. In its most basic form, as a framework for cryptocurrency, a blockchain is a ledger which stores transaction data. It can also be used for other purposes, but today when we talk about blockchain, it'll most likely be referring to it in the cryptocurrency context. So if we've defined our blockchain like this, you might ask, what's the difference between a blockchain and a database? Well, first of all, the main difference will be the structure in which the data is held, which we'll talk about later. But first, we should talk about what a blockchain aims to be and how this sets it apart from a traditional database. Decentralization and immutability. These are two core properties which most blockchains aim to incorporate within their structure. The majority of our current internet technologies work through a centralized system. This means that clients connect to a server. Clients tend to not directly interact with one another, and most interactions involve the server in some way. For example, databases will be hosted on a dedicated server machine, with clients getting and putting directly to the server. On the other hand, blockchains are distributed across many different nodes. Each client is also a server. Everyone interacts with one another in a peer-to-peer manner. This means that the data is distributed all across the system. Decentralization is important as it means that as long as the system itself is being used, it will stay up. As long as there are nodes willing to be called upon, the system is maintained. Meanwhile, centralized systems require support from the host. If the singular host discontinues their services, the system will end. As mentioned before, another important property is immutability. It is defined as the state of not changing or being unable to be changed. In terms of our blockchain, this means that once we add data, it will be stored permanently and cannot be altered. These two properties are achieved through the blockchain mechanism, which we'll explain briefly. So how is it done? As we talked about before, data in the blockchain is stored as blocks. Blocks linked by storing the hash of the previous block, which forms a chain. If we change the data within a block, the hash value of the block will change. This means that if you modified a past block, the stored hash in the next block wouldn't match up, which ensures immutability of the data. In the cryptocurrency example, the blocks store transaction data, which you might call a ledger. Blocks also store headers, which may contain things like timestamps and other valuable data required for the chain to work. Now that we have the data structure, let's talk about the logistics. The blockchain system is able to self-govern thanks to the hashing system and distribution of data. Everyone can access all the data as a local copy or request it from one another. When a node creates a block and adds it to the chain, it can communicate this with its fellow nodes, which can verify whether or not this block is valid. The process of the nodes agreeing is called consensus. Different blockchains may decide on different methods of consensus. The two main chains that will be discussed in this video are Bitcoin and Ethereum. To give a short summary, Bitcoin is a cryptocurrency which uses the blockchain as a distributed ledger. Though Ethereum has its cryptocurrency, the primary value in the chain is to act as the mechanism behind the Ethereum virtual machine, also known as the EVM, which is a sort of distributed computer. Let's talk about the consensus mechanisms behind them. The blockchain community or developers will decide upon a certain rate at which they want the blocks to be created and sets the mechanism so that the blocks will be produced at this rate. In proof of work blockchains, this means setting a difficulty for a computational problem which block creators must solve. These block creators are called miners. They're also nodes in the system. For example, in Bitcoin, the computational problem involves finding a number which, when hashed alongside the rest of the block data, produces a block hash below a certain value. Any node can verify that the miner has done the work correctly by simply hashing it themselves, thus being able to prove their work. Alternatively, some blockchains decide to do this with a proof of stake system. This is when a validator is selected at random to create a new block. Then, fellow validators can vote on whether or not this node is valid. Nodes holding a larger value of currency or stake have a larger voting weight than those with comparatively less stake. Nodes vote and reach a consensus on whether or not a block is valid. In a proof of stake system, instead of the difficulty determining the block rate, the delay between the blocks is fixed. While less commonly discussed, there's also a mechanism called proof of authority. This is really only used in private blockchains and requires a trusted set of individuals. In order for the system to work, we need nodes willing to perform the action of miners. They're needed in order for the system to work as they're the backbone of the whole system. Blockchain systems incentivize these miners by offering them rewards in the form of gas tax and block rewards. Gas fees are the term we use for transaction fees, which take cryptocurrency amounts off of every transaction done. In systems like Ethereum and Bitcoin, not only are there rewards for mining a block, it also costs gas to transfer currency or requests actions to be completed on the EVM. This fee is set by the miners, and those involved in the transaction must pay the fee. As blockchains are being implemented to a greater extent worldwide, we begin to run into some problems. The blockchain trilemma refers to an inherent difficulty in blockchain to support these three properties at once: decentralization, security, and scalability. While it's commonly agreed that decentralization and security are core to the identity of a blockchain, scalability must also be present in order for widespread adoption of a chain. The most well-known chain, Bitcoin, has high security yet has slow transaction times and faces issues with large mining pools controlling big portions of the computational power. Ethereum is working towards a proof-of-stake model to improve upon all three of these aspects. Layer 2 chain solutions may be implemented to improve the performance of a blockchain. While Layer 1 refers to the blockchain mechanism itself, Layer 2 refers to solutions that may be implemented off the chain but interact with it. This may come in the form of making transactions off-chain, bundling them together, and putting them back on the chain secured by proofs. This helps with scaling, as this increases the number of transactions without increasing the number of blocks needed to be mined, increasing speed and scalability. A smart contract is a set of instructions which can be executed on nodes. It can be thought of a program just that it's executed on the EVM nodes, and storage is within the Ethereum chain. Smart contracts reside within their own addresses in the Ethereum system, and its code can be seen by anyone who wishes to see it, which ensures transparency. Smart contracts add another layer of usefulness into a blockchain, giving it a more complex use outside of cryptocurrency. It allows us to build decentralized applications, which might be part of what you guys will be building in the upcoming hackathon. Hope you guys found this short review of blockchain interesting. If you have any questions about some of the topics we covered, feel free to put a comment down in the description.